Can you also yes. I'm preparing the you talk with the so teaching assistant. Yes. You can like I have to prepare this. Yes. Can you approach? I have to prepare. Okay, the lecture. Yeah. Thanks. All right, so let's start our class today. So today is new topics, so different from the two previous topics, I guess. So remember that in the beginning, we have four different kind of themes, or I call it pillars. Four pillars of computer vision. So the first thing that we discussed in the earlier in the lectures was object detection. Well, it is object detection / recognition. So this is one of the most important pillars in computer vision, right? So when we have the object detection, one of the specific topics that we discussed was face detection. And the second pillars that we discussed was geometry. And in this case, we discussed a specific techniques, which is stereo, depth from stereo or depth from video. Depth from stereo or video. So this is the two pillars that we have discussed. And today we discuss on the third pillar, which is motion analysis. And in this specific example of motion analysis is optical flow. So this is somehow the bigger picture of this topic today. And later on, after motion analysis, we will discuss about low-level vision. Low-level vision means the other word for low-level vision, or the other term for low-level vision, is image processing. Okay, so this is the 4 pillars that we will discuss, or the 2 remaining pillars that we will discuss in this remaining time. Okay, so let's focus on optical flow. Now, the question is here in your mind, if you heard this optical flow for the first time, is that what is optical flow, right? What is optical flow? So basically, optical flow capture moving objects. So if I move my hands here, for example, then the motion is on the from left to right or right to left, right? So this kind of motion that we have a direction of this hand, in this case of this object, and also the speed. So if I move here, it's the same as I move there in terms of the direction, but the speed is different. Okay, so in motion, you have this information, the information of the direction and the information of the speed. So basically, motion is a vector, because in a vector you also have 2 types of information. One is the direction, and the other is the magnitude. And the magnitude here represents the speed. And it's very important in computer vision, especially in many applications like self-driving cars. If you have a self-driving cars, right, and then you see the other side, there is a car coming to you, then you want to judge whether this direction is on to you, the direction of the car is onto you, and how fast this car is moving to you. Right? So this information is very important, because if you know that the direction is on to you, towards you, then you can avoid this collision. And you can also know how fast this car, so then you can take necessary action to maneuver as soon as possible. So the information of this optical flow or the motion is very important for many different autonomous agents or autonomous machines. Right. So specifically, optical flow is about the apparent motion. So this is about apparent motion. I'll explain further on what it means by apparent motion. Apparent motion of brightness pattern. And this definition of apparent motion is different from motion flow. So this is not the same as motion flow. So I will explain the difference between optical flow as apparent motion and motion flow. I'll give you an example here. So for example, if I have a ball, right, and there is a stick on the ball, so the ball is attached to this, the stick is attached on the ball, and this is the ball. And assume that the ball is textureless. So this one is a textureless, means that there's no texture. You can assume that the ball is totally white or totally black or totally red. And then you move this object. You move that object. So you move the stick. And then you take picture or take video of this motion. It's totally pure white or totally pure red or whatever color you want, but it's textureless. Okay. So when you see from the video, Do you see any motion? Do you see that the ball is moving? No, right? So of course there is no highlight. In this case, I put highlight here to see that it's a ball, but actually there is no highlight because this ball is actually a diffuse object. Diffuse object is object like this one. This is called diffuse. There's no highlight. There's no glossiness on the surface. If it is glossiness, then you can still see somehow the object moving. But if you don't have the glossiness, that doesn't have the specular highlights, something that diffuse or made object like this, then you will not be able to see that the object is moving. So if there is no object, the appearance of the object is not showing any motion, that's the meaning of optical flow. Okay, so that's why this is apparent motion. So for this case, this one is not optical flow. Optical flow will not be able to capture the motion. Okay, so this is not optical flow. This is beyond optical flow because optical flow will not be able to give you any information, any motion information. But this one is actually non-zero motion field. Non-zero motion because physically it's moving. Physically it's moving, but you cannot see it that it's moving. So that's why this is called zero optical flow. So it's not optical flow. In other words, it's called zero optical flow. But it's non-zero motion. So that's the difference between optical flow and motion flow. Motion flow is about physics. It doesn't really matter how it looks like, but it's moving. Okay? Any questions on the difference between this optical flow and motion? All right, so there is the first difference between motion flow and optical flow. Another difference is that this particular example, assume that you have a ball, and in one image, you take a picture of one image, and the light is from here. It's textureless, but there is a specularity here. Or maybe if this made object is fine, made object is also fine. It is made object. Assume there is a made object. Made or diffuse object. Without glossiness, without specular reflection. So in this case, it's likely that there will be some self shadow. You know, it's like a moon. If a moon, you see the moon somehow. Sometimes it's a house, right? That's one is because of self shadow, and in self shadow means that you have self shadow there, right? That will be the appearance when you have this kind of lighting. Now, then the second image, you turn this off, you turn that off, and you move or turn on the second light. In this case, the shadow will be here. Okay. So in this case, the motion, there is no motion. So this one is actually zero motion. Because there is no motion of this object. But this one will be non-zero optical flow. Optical flow will give you some information about the change of the light. And of course, in this case, optical flow is wrong. But it's inevitable. You know, because the data seems like it's moving, although this is not a moving object. And that's why this is called apparent motion. It seems like moving, or it seems doesn't move, seems not moving, because we are relying on the appearance. Any questions here between the difference of these two? Right. So I can give you an example here of optical flow. Let me see if I can show you. All right. Today is will be a lot of mathematics discussion. Please be prepared. So this is called optical flow. It is not from a single image. It actually we have two images at least. And if you have two images, then you can compute the flow. And this flow is actually three-dimensional data. Let me see. Yeah, so but it's encoded into this color. So this color encoding will represent the direction. So if the movement is red, this one is red, somehow red movement, right? So this one is kind of reddish movement, or maybe not really red, but somehow orange in the between orange and red. So it will move in this direction. If this is green, it moves in that direction. If this is white, then there's no motion. Okay, so there is the color coding here about this optical flow. Okay, and the other thing is that this color have this magnitude here. So if you get into this color, for example, then this magnitude here is represent the speed. So the color itself represents the direction, but the distance of the color to the origins of the center represent the speed. So there are three different information: the direction and also the magnitude. Any questions here on the color coding? If you don't understand, please ask, because this is very important. The whole discussion today will rely on this color coding. Any questions, anyone? Yeah. So there are many, as you can imagine, this is very important again for many different applications. Object tracking, motion analysis, collision detection, image registration, which is image alignment, all can be effective or efficient if you use optical flow. Okay, so now let's move on how we can compute this optical flow given images, right? So one technique that we will discuss in this optical flow computation is Lucas and Kennedy. Lucas, Kennedy, optical flow. Okay, so one thing that is in the optical flow, a basic assumption on the optical flow is called BCC. BCC stands for brightness, constancy, constraint. So maybe you notice here that today I'm a bit slow. I deliberately doing this because otherwise there will be too much material for you to learn from. Hopefully we can finish the whole lecture today with optical flow only. So then next time we can keep up with the syllabus, not necessarily go beyond the syllabus. Okay, anyway, so this is about brightness, constancy, constraint. So what is the brightness complexity constraint? The brightness complexity constraint means that the brightness of the object, brightness of the object, or the target object in this case, at one frame and a frame after that, and the next frame, is identical or doesn't change. So this is the basic assumption. It means that if you take this picture, the picture of this pen in one image, and then the next image, you take the same picture of the pen, the pixel intensity on this pen are assumed to be the same. It doesn't have any changes in the brightness. It doesn't work for extreme cases. For example, when you take this picture here, and then suddenly you turn off the light, for example, and then you take another picture, that the BCC will be broken. Okay, only when they are the same, then the BCC can hold. Okay, so let's interpret this mathematically. So assume that the pixel brightness can be expressed as I, X, Y, T. I is the intensity, in this case, grayscale pixel. X is the location in X and Y coordinate in your image. And T represent the index of the frame. Right? So if you have two images, then T equal to 1 and T equal to 2 next to it. So under BCC, it means that I, X, Y, T in one frame, T equal to 1, for example, equals to I, X plus U, Y plus V, and T plus 1. Because the object assumes to be moving. U and V is the vector of the movement of the object. So if you want to imagine this, so this one is frame 1, and the object is here, for example. This is T equal to 1. And the object moves in frame 2, T equal to 2. And this vector of the red arrow is U and V. So this one here is U, this one is U, and that one is V. Any questions here? Right, so that U and V here is something that we call U and V here is to become a vector. It's called optical flow. So that's the definition of optical flow, the motion vector. And that's something that we want to find. U and V is something that we want to find. So again, this one is called optical flow or optical flow vector. Okay, so let's have get into this notation here. I, X, Y, T. If I do the derivative of this X, Y, T with respect to dt, then I can apply a chain rule. if I apply chain rule, then Ti divided by Tx, and then Tx, T plus Ti, Ty, Tt plus T, and because you say that this one is actually equals, because this one is equal, the change in terms of the time will be 0. This is also called PCC. That the rate of the change in terms of the time equal to 0. It's exactly the same. These two equations are exactly the same. Right. So let's look at the more detail of dx and dt. So dx dt equals to, in discrete, we can discretize it to delta x divided by delta t. The change in x and change in divided by the change in t. And delta t means that x t plus 1, the next frame, minus x t divided by t plus 1 minus t. And this one, xt plus 1 is xt plus, in our previous definition, is plus u, because we have the u vector or u direction, u interval, minus xt divided by 1. And it is equal to u. So dx dt equals to u. And we can do the same for dy dt. And as a result of this, di dt equals to di, or I can put it into simple notation, ix multiplied by u plus iy multiplied by v plus di dt it equals to 0. Is it okay? In other words, well, if this one is actually the equation that we are looking at. So this is the implication of BCC, brightness constancy constraint. Right. And Lucas Canade is looking at this equation. Lucas Canade is, because this one is equal to 0, means that if we have ixu plus iyv plus it ideally equals to 0. But sometimes it might not equal to 0 because of noise and so on. But it means that we have to minimize this equation. We minimize this equation with respect to what? What is the variable that we want to change to make it 0? U and V. U and V. So we change U and V, or we find U and V in such a way that this equation should be minimized, should give you a minimum value or number. And if you want, you can put argmin here. In this case, if you put argmin, then the output here should be U and V. U and V for every pixels. Or if you use mean, then we can just say that mean of E U V with respect to U and V equals to, well, mean U V, the equation here, Ix U plus Iy V plus It. And in this case, normally what people want to do is to have function E that's easier for us to minimize. And a function that's easier to minimize is what? Convex function, exactly. So convex function will be easier to minimize. And convex function here in this case will be what kind of function that I have to apply in order to get the convex function? Is very basic. Is square, exactly. Is quadratic. Quadratic is a convex function because quadratic means that it's something like this, convex. Right? Okay, any questions, anyone? So this is the function that Lucas Canada is looking at to minimize. So now the question is, how can we do this? How can we minimize this? So if you want to minimize this function, so now minimization. If you want to minimize this function, basically you want to minimize E, right? The function is E. This function is E here. That's the function that we want to minimize. So if you want to minimize the function E, what do? We know that it's convex. So what do? It's very basic pattern recognition questions. So what do we do here? Derivative, exactly the derivative of dE du equals to 0. And dE dV equals to 0. And that's the solution that we are looking at. Okay, so now let's look at dE du. dE du equals to what then? Anyone? dE du equals to 2 times Ix is very basic derivative. Ixu plus I1 V plus IT times Ix. Yeah. Equals to 0. You can do the same for Iy. So now we have two equations, right? One is with respect to U, the other is with respect to V. Okay, so let's look at the two equations. So in the end, we have 2 Xu plus Iyv plus It equals to 0, or multiplied by X equal to 0. And the other one is 2 multiplied by Xu plus Iyv plus It multiplied by Iy equal to 0. So we have two equations here. And we can cancel this out, right? Because that will be meaningless. So if we cancel that out, then we can transform this into a matrix operation. X multiplied by Ix, Iy multiplied by Ix, multiplied by U and V. This will give you this part here, right? That true? Yes. Multiplied by this one, of course. Multiplied by the Ix. And Ix, Iy equals to minus what? ITRX multiplied by, the other one is ITIY. So in the end, what do we want to find? What is the goal here? To find what? U and V. So if you want to find U and V, what do you do then? What do I do here? What is the next item here? The inverse of the matrix here, right? So I invert that one. So Rx, Rx, Iy, Rx, Ix, Iy, 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 inverse multiplied by, or this is minus, IT, X, IT, Iy. Done, right? We have the solution for the optical flow for every pixel. Any questions here? This is the end of the story. Sorry? Exactly. Is it invertible? Right? The next question is, is it invertible? What do you think? Is it or not? So assume that this is the whole thing here. The whole thing here is A, matrix A. So now the question here is A invertible? So what is the criteria of a matrix to be invertible? One, it has to be squared. Right? It's square, yes, it's squared. But not every square matrix is invertible. And the second criteria is what? Full rank, yes, or the determinant. Yes, the determinant of A is not 0. So the determinant of A should not be 0 to be invertible. Now, what is determinant? Yeah, so what is the determinant definition? In this case, will be Rx, Iy multiplied by Iy, Rx minus Rx squared multiplied by Iy squared. This one is, the left part is Rx squared multiplied by Iy squared minus X squared. Iy squared equals to 0. So it's not invertible. So not as easy as we thought. Optical flow is not as easy as we thought, because this one gives you 0 determinant, which means that it's not invertible. Now, if it is not invertible, what can we do? So the solution here now, this solution is proposed by Lucas and Kanade, is that instead of pixel operation, the one that I explained to you is actually pixel operation, local pixel operation, right? And here is that instead of pixel operation, we use patch space operation. So use patch, basically. So how we can use patch? If you use patch, it means that, for example, the easiest one is 3 by 3. And the flow that you want to find is the flow of this pixel here in the middle. And you try to find, of course, there is another image here. And it happens that, it moves up to that direction. So of course, this is different location. This patch is different location. So you imagine that it's part of the bigger image. So typical image here, and the other is the image here, and basically it moves to that position, right? So we have 3 by 3 patch in our analysis. So it is 3 by 3. Let's assume we have index here. So let's assume that we have index. So this one is 1, 2, 3, 1, 2, 3. So we put index there. So let's assume that 1, 1. 1, 1 means that I. So we have I at the location of x, 1, 1. Ix, the derivative with respect to x for 1, 1 pixel. 1, 1 pixel is here. There is 1, 1 pixels. And we find the derivative of that. So I just follow which one? Yeah, I follow this equation here. So I follow, I use this equation here. There. Okay, so I use the first equation there. I put x1, 1 for every pixel in the patch. And then I multiply it square because you multiply with ix. And then I have u plus I y1, 1 multiplied by ix1, 1 multiplied by v equals to minus it1, 1 ix1, 1. Agree with me? Is it correct? Okay, so that's for 1 pixel at the corner there. So we have to do this for every pixel. So we, in the end, we will have 9 equations. Okay, so I got the second one. Ix1, 2 square u plus y1, 2 x1, 2 v equals to minus it1, 2 x1, 2. So I do this for every pixels, 9 pixels, and then I sum them. And if I sum them, then this one will be the sum of I and j. I and j is the I is this one is I, then that one is j in that patch. Okay? So there's the patch index, the pixel in the patch. Xij square multiplied by u plus the sum of ij, iy, ij multiplied by ix, ij multiplied by v equals to minus sum of ij, ij multiplied by ix, ij. Agree with me? Okay. So this is called patch space operation for optical flow. Now, if you convert this into a matrix form, then we will have sum over, this one is sum over ij, xij square, sum over ij, xij, iyij. So this one is the same. Ij, ix, ij, iyij, ij square, right? Equals multiplied by u and v equals to minus sum over ij, ij, ix, ij, sum over ij, ij, iyij. Now, the question is it invertible? Is that invertible now? Will it give you determinant equal to 0? Anyone? It is yes and no. It is yes if the surface, if the patch 3 by 3 is textureless. If it is textureless, the sum, the derivative in Ix, remember what is Ix, right? You know Ix, right? Ix in discrete is what? Ix plus 1 minus Ix. So this is in discrete. And if you have textural surface, Ix equal to what? If the surface is like this, Ix equal to 0 because the difference between the pixels are the same. So this one equals to 0. It is textural surface. So if textural surface, it becomes 0 here, it's 0 there. And it's likely that this one is 0 and this one also 0. So everything is 0 on the left. So for textural surface, it's still unsolvable. But even for human, it's also unsolvable, right? If an object move white, white chameleon, chameleon can change color depending on the object, right? One white chameleon move from here to there, you cannot see, right? So, and the same problem here. But if the object has some boundary like this, for example, then it's likely that Ix will not be equal to 0. And if Ix squared will give you some value here, Iy squared give you some value, maybe 0 for that particular case, right? Or maybe if it is a sum of them, maybe there is some value that is not 0. And the Ix squared is different from the sum of Ix. It's not likely to be different. So for edges, for object with boundaries, we can still see the motion. We can still capture the motion using this patch information. So in the end, if you look at the optical flow information, if you compute using this patch space, it's something like this. So the line represents the motion of the pixels. So if the object is textureless, like this part here, for example, then it cannot be computed. So the object here, for example, also cannot be computed because it's somehow textureless. But the other parts that are not textureless, you can compute the optical flow. You can see the motion. The motion here, you have to be careful, it's not necessarily to be the motion of the objects, but also the motion of the camera. If both of them are moving, then the motion of the optical flow represents the motion of the camera and the motion of the object. But if the camera is static, fixed into a tripod, for example, then the information of the motion is only the motion of the object. Okay. Any questions here? So in a self-driving car, for example, because your car is likely to move and the other car is also moving, right? You have to compensate the information by canceling your information, canceling your motion, your self-motion. Once you can cancel the self-motion, then you can know the speed and direction of the other car. Any questions, anyone? So this is the easiest part, which is called optical flow. And as you can see here, the optical flow is computed locally. It's a local operation, means that this optical flow here, the flow here, is only computed in this patch. It doesn't really matter the car motion or the other object motion. is only local most computation. And that's the reasons that Lucas and Kennedy optical flow is called local motion optical flow. And it's also sparse, right? As you can see here, it's sparse because edges or non-textural surface is quite sparse. If you see the world, most of them are textureless, aside from certain part, which is not textured. So that's why optical flow, Kennedy optical flow, or Lucas Kennedy optical flow, is a sparse optical flow. And it's different from what I showed you before. So what I showed you before here, this one is called dense optical flow, because we have to compute every pixels in the image. And this is something that we want, actually. Most applications want to have dense optical flow. Well, depending on the application, of course, but many applications need to have this dense optical flow. And Kennedy cannot give you dense optical flow. It can, but it has many different algorithms, further algorithms to do this. And for that reason, we will continue our discussion on another techniques of optical flow called Horn and skunk. Horn and skunk optical flow. So this is a competing algorithm between the two: optical flow of Lucas and Kennedy, and Horn and skunk optical flow on the other side. And actually, this is also competition of two universities until now. Lucas and Kennedy is from CMU, Carnegie Mellon University, and Horn and skunk is, you guess, from MIT. Right. So this is two competing top universities in computer science, in computer vision. Until now, they are still competing between MIT and CMU. Right. So Horn and skunk is from MIT. So this one is MIT faculty. And right. As I mentioned again, Horn and skunk is actually more practical, it's more used. So you know, if you follow research, normally you will know about this Google Scholar here, right? So if I look at the Lucas, Kennedy, Lucas and Kennedy, this is 2% actually. Let's see, Kennedy and Takeo Kennedy. Takeo Kennedy is from Carnegie Mellon University, and I think the optical flow here is number one of the citation. So the citation for optical flow, which is iterative image registration techniques, published in 1981, is cited 17,000 times, 17,800 times, which is quite a number, right? It's not easy to get citation. So this citation is quite high. Now let's look at Horn. BKP Horn. So that called Horn is also published in 1981. Is determining optical flow is also 1700. So they are competing each other. Okay. Anyway, so this is just a side information. Okay, so let's look at the Horn and skunk algorithm. So the objective function is the same. Objective function so there's a sad story as well for this Lucas and Kennedy. Canada was famous since back then. In 1980s, already famous. And this Lucas is his PhD student. And Lucas, I think, is the one that devising this algorithm, right? I mean, the main brain is Lucas. And Lucas showed this to him, the derivation. And Canada said that it's too simple, right? And he doesn't believe that it will be famous or anything. He just put aside, okay, publish there, and he didn't think too much about it. But in the end, it becomes one of the highest citation of his. Right? So sometimes that happens in research. You don't think that it is something that's useful or it is something that is powerful, but you can use later on. You see that actually it is very useful. Right. So for instance, the objective function of E, U, V is almost the same. It's IX multiplied by U plus IY V plus IT squared. So this is a quadratic function as well. But this is a clever thing about, for instance, they put a prior. So this one is a data term. So this one, as you can see, if you learn about Markov polynomial field, it's a data term. Or if you follow or if you take pattern recognition course, it's actually likelihood because you involve the data. I is the data. And you have alpha here or lambda, in the previous notation is lambda. The prior. And the prior here, remember what is the prior that we like to use in the previous discussion? What our prior? Smoothness prior, right? So smoothness prior is very powerful in computer vision because most likely the image is smooth, like the surface is smooth, and this kind of surface is everywhere. So we force this to be smooth, means the optical flow has to be smooth. What does it mean that optical flow is smooth? So if you have an object, right, this kind of object, if you move this object, it's likely that the whole surface will move. It will not, dispersed. This surface will not be dispersed, not unlikely to be dispersed. It's likely to be unite and move. And this is some kind of motion means that U and V, the vector representing the cup or representing this bottle there, have to be smooth. If one pixels here go to that direction, the rest have also, or the neighboring pixels have also moved to that direction. So this is called smoothness motion constraint. So you make the derivative or the gradient of U to be smooth. You minimize this. Means that we encourage the gradient of U to be 0. The gradient of the motion to be 0. It means that the surrounding U have to be the same. Another one is, of course, V. The gradient of V squared also encouraged to be 0. We minimize E. Remember, we minimize E. So this is called smoothness prior. So what is this nabla U, right? So this one is called nabla U, I think. Nabla is a vector. It's a gradient vector. So gradient vector means that you have du dx, du dy. So imagine that your U is a U map. You have a map representing the value of your U, of your pixels. So this one is correspond to your pixels, the map. So the motion of U in the x direction for each pixel. And then you also have V map. And V map is also a map. And the resolution of this map, again, is the same as the resolution of your image. Okay. So if you want to know the motion of this pixel here, for example, then you can just take the U value there and the v value there. Then will be the u and v for that particular pixel. Okay. And because you have the map, then you can do the derivative. You can have du dx, du dy. And you know the meaning of the du dx, right? This one means that u x plus 1 minus u x. This one is, of course, you have to have y minus u x y. That's the meaning of that. And you also have u x y plus 1 minus u x y. And this nabla u, we can shorten the writing u x u y. Any questions here, anyone? And you have this notation of u, this one is a square. It means what? It means that without square, it means the magnitude. Because u and uv, or nabla u here, nabla u here is a vector, right? It's a vector, ux, uy. And this one, the two straight lines, means the magnitude of that vector. How we can compute the magnitude of a vector? Square root, yeah, square root of what? In this case, nabla u is equal to ux, y. Ux squared plus uy squared. But then we have squared there. Means that you square this. And this one becomes ux squared plus uy squared. And again, if you look at this equation, there, that's the meaning of that one. Ux nabla u squared means that ux squared plus uy squared. And we want to minimize them. We want to minimize these two here. Means that ux squared have to be minimized, uy squared to be minimized, means that the entire is to be 0. And that's why this is called smoothness constraint on the motion. Any questions here? Again, if you don't understand, please ask, because this is very basic. And as I mentioned in the beginning, there will be a lot of mathematics. Believe me, when I say there's a lot of mathematics, it's a lot of mathematics. Right? So make sure that you understand at this point. If you don't understand at this point, please ask. Okay, good. I assume that you understand this. So now, the good thing is about Horn and Scrum is that they try to do the global optimization, not just pixel by pixel optimization, but the whole image, the whole map optimization. So in this global optimization, what we want to do is not to minimize just EUV. What we want to have is to have J UV, means J is the error function of UV, for the whole EUV. So it's actually two integral. In this case, it will be two integral. Right? What does it mean by this? It means that, integral in discrete means what? Integral in discrete means sum. It's actually sum of all the errors in X and Y. Means that we don't really care about the minimum value in that particular pixels, as long as the whole image gives you small value. Okay, so this one is called global optimization, means that we want to minimize the whole image, not up to the individual U or and V. U and I mean U value for certain X can be higher than Lucas and Canade value, but the whole picture have to be small. When you sum them, have to be minimum. Any questions here for the intuition of the global optimization? And this is the questions that Hon and Skang try to solve. How we can do the global optimization. So the question here is how. Okay, so fortunately, in the field of mathematics, people thought about this long time ago. Okay? And the solution for this can be found many years back by Euler and Lagrange. So Euler and Lagrange already solved this problem. And the solution is called Euler-Lagrange equation. So this is the solution. Okay, so how many of you know about Euler-Lagrange of solution equation? Well, not many. Okay, so I will try to explain this. Euler-Lagrange equation. So assume that we have J. J is a global cost function that we want to minimize, and assume that we have a function that we also want to minimize. The sum of this we want to minimize, and it's a function of y prime, or the derivative of y, and t dt. And here y prime, the derivative of y is dy dt. And according to Euler-Lagrange, J will be stationary. Stationary, you know, stationary means that it will be on the peak. It will be stationary. If so, this is I don't want to prove this, but this is already proposed by Lagrange. Df dy minus d dt of df dy prime equal to 0. So this is actually the solution. And we will use this equation to solve the optical flow problem. So let's try to understand the solution here. How come this become a solution of that error function? So let's look at the simple example. So assume that you have 2 points, A and B. Now the question here asked by Euler-Lagrange at that time, what kind of shape that connecting A and B that give you the shortest distance? It is a straight line. We know that, right? But why? Why is a straight line? How can we prove that it will be straight line? Why not this one is something like this? Or something like this? Why this has to be straight line? So they try to prove this. Okay, so they try to prove that it will be a straight line mathematically. So to prove this, assume that you take the blue road. So the blue route is something that you assume that you will take, that the shortest distance is the blue line. And in that case, you will have a certain distance here called delta S. So delta S is some distance of the line. So, and in that case, S should be like this. So this is delta S. And if you look at the Y and X, so this one is Y, this is X. So you have delta X and delta Y to represent delta S. Okay. And delta S here approximately is a square root of delta X squared plus delta Y squared. We can approximate that. This is approximation that very, very small should be approximated by a line. The blue line is not necessary to be a line, but a small segment in this blue line must be a line. Or can something that can be approximated by a line. Okay, so based on this, then we have Ts equals to dx squared plus dy squared. And ds equals to, let me see. If you multiply by dx and dx multiplied by dx squared plus dy squared, then let me see. It can give you dx squared divided by dx squared plus dy squared divided by dx squared multiplied by dx. Correct? So then I can have the integral of ds, and I can have this integral of that particular term. So I have integral here as well. Correct? So now, if I do the integration for ds, it gives you what? It gives you s. And you do the integration of that, so the integration of square root of 1 plus y prime squared. Right? Multiplied by dx. And s here, if you look at s is actually the entire road, the entire line. If this blue line, then s is the blue line. If this the red line, s is the whole red line. So s here is something that we want to see. Whether this s, what is the equation of s? Whether this, if the equation is linear equation, then it will be a straight line. If the equation is quadratic, then it's a quadratic line. So we want to see whether s, in the end, if you do the derivation of this, give you a linear equation or not. Okay, so that's the goal. So we want to solve this. We want to solve the right term. So the right term here is similar in the form to Euler-Lagrange equation. So if you compare this and this, they are similar. We are already in the same form. S here, of course, is J. Okay. So if you look at it, if you follow the equation, so F is actually a square root of 1 plus y prime squared. That will be F. X will be T. And okay, so we have to follow the the Lagrange equality here, the Euler-Lagrange solution. So we apply that equation there. So number one, df dy. So we compute this term here, df dy. So what is df dy in this case? What would be the output of df dy? Do we have y in f? Do we have y in f? We don't. We have y prime, df dx, but we don't have y itself. So if you do df dy, it equals to 0. That's the first term. The second term, which is the second term is bit complex. So first we have to have df dy prime, right? So we do df dy prime. What is df dy prime? Anyone? What will be df dy prime? So this one is d dy prime of square root of 1 plus y prime squared equals to what? This one, if you remove the square root, is actually power to half. And if it is power to half, then it will be easy 1/2 multiplied by itself 1 plus y prime squared. Is that true? Yeah. Multiplied by 1 minus half. Multiplied by 2 y prime. Anyone agrees here? Okay. So then the f dy equals to this one is cancelled. So this one is cancelled. Then we will have y prime divided by square root of 1 plus y prime squared. That will be df dy prime. But then we have to do the further derivation on d dt. And t here is the same as x. Okay, so in our case, x t equal to x. So the third step is to have d dx on y prime 1 over y prime squared equals to what? Anyone? Is there any x in the equation? No. Then equals to 0. Okay, so now let's look at the whole equation. So df dy, let me see. Let me see. Okay, so let's look at this, the third equation. df dx dy equal to 0. And this equation here can be seen as ODE, ordinary differential equation. So what does it mean by ODE? In ODE, the simple case of ODE, is that dy dx equal to 0. This is the simplest case of ODE. And then what you need to do is to put dy dx equals to integral of 0 dx. Correct? Anyone disagree with this? So on the left, give you what? This is cancelled, right? dy integral of dy give you equal to y. Y Is it only y? Well, plus c. And on the right, equals to what? 0, only 0 is also c, c1, c2. So in that case, in this solution, in this example, simple example, y equal to c. You can have y that is equal to c. So for our case, here, the same way of thinking. So let's look at this equation here. So let's look at the equation there. So if you want to solve this using the same equation, so we integral dx y prime 1 over 1 plus y prime squared dx equal to integral of 0 dx. So we cancel this out. The integral of d dy is dy y itself, right? So you can have y prime square root of 1 plus y prime squared equals to what? Integral of 0 dx t. Agree with me here? Okay. Now we can have y prime. Oh, by the way, it's yeah. So it is actually plus c as well, but in the end, c going to that way anyway. So it's c. So it's going to be much better. So y equals to c multiplied by square root 1 plus y prime squared. And this one, if I put c inside, it's c squared plus c squared y prime squared. And this one becomes y prime squared equal to c plus c y prime squared. Oh, c squared. C squared. Well, c squared is c. So let's remove this one because it's c anyway. So y prime squared 1 minus c equals to c. Agree with me, this one, right? Okay, almost there. Y prime y prime, which is dy dx, right? Equals to square root of c 1 minus c equals to c. Yeah. And we integralize this one, integral 31 dx and dx here. So we remove this one, cancel that out. So what we get on the left? Y plus c, right? Equals to what? C x plus c or d, right? What equation is this? Linear equation. That's why it is a line. Yeah. So the shelter system of 2 points in the Euclidean space is a line. So that's how we use this equation of Euler-Lagrange. And we apply this for optical flow. So you can imagine that for a line it's quite complicated, right? Let alone later on we will see for optical flow. But anyway, so let's any question for this? Again, this is how we use Euler-Lagrange equation to solve global optimization. Okay, so if there's no questions, let's look at the Horn and Skun global optimization. So again, the objective function is J U V. So J U V, the integral of E U V dx dy. But you know that there are actually two integral signs. And U E U V equals to Rx U plus Iy V plus It squared plus lambda nabla U squared plus nabla V squared. So using Euler-Lagrange equations, then we have, according to the equation Euler-Lagrange, F here is E, so dE du minus d dx. Again, t is in our case is x here. dE dux minus d dy dE duy equal to 0. So this is called Euler-Lagrange equation for two-dimensional space. Previously, we only have t, one dimension, but now we have two-dimensional space u and v. And that's the first equation. The second equation is dE dV minus dx dE dvx minus d dy dE dvy equal to 0. If you can solve one of this equation, you can solve the other equation quite easily. Okay, so let's focus on one of them. So let's focus on this equation here. Okay, so if you focus on this equation, one thing that you might have a question in your mind is what is this, right? What is this equation? What this term means? That equation is quite complex there. So that equation is d dx dE dux equals to d dx d dux. If you look at E, right? E is E here. If you look at E, E is actually this equation here. So this E refers to the E. So, and we want to do the derivative based on ux. So where is ux in the equation E? Definitely it's not here, it's not there, it's not here. I think there's nothing here because there is this p term, but there must be somewhere here. Right? So remember that delta UP is actually nabla U square is actually UX square plus UY square. So UX is actually there only for that particular term. Right? So if you do the derivative for on E with respect to UX, then what will be it? What will the equation that you get here? Alpha will still there, I think. Multiply by so let me see. This one actually ux2, right? The ux squared. So this one should be the derivative. Yeah, this is ux squared then dx of 2 alpha ux. And that you have to do the derivative with x. 2 alpha u x x. The second derivative of u. Any question, anyone here? So that's for that particular term. So let's look at the whole equation here. dE du, the first term here, dE du equals to what? Where is u? U is only in the first term, right? Only here it does have u. The rest doesn't have u. So you will have 2 multiplied by xu iyv it multiplied by ix. And then the second term, we know the second term already, which is 2 alpha uxx. And then the third term is similar to the second term, right? That will be 2 alpha uyy equals to 0. Anyone disagree with this? Okay, so, and if you simplify this, then we can have 2 multiplied by xu plus iyv plus ix minus 2 alpha delta u. Well, delta u equal to d squared dx square u plus d squared dy square u. In other words, this one is equal to uxx plus uyy. All right. Okay, so by the way, there is a name for this. Anyone knows the name of that? Delta U? Laplace operator. That's right. This one is Laplace operator. Okay, so then if you look at the whole operation here, if you combine 1 and 2, 1 is already there. So 2 xu plus iyp plus it multiplied by ix minus 2 alpha delta u equal to 0. Number 1. And number 2, iyp plus it iy minus 2 alpha delta u equal to 0. It reminds you something, right? It reminds you to Lucas and Kennedy. But again, this has to be solved globally, and we cannot follow Lucas and Kennedy to solve this. Okay, so now, before we get into the optimization part, let's look at this definition of Laplace operator here. Sorry, this one is not in view, but okay. So let's look at the delta u. So if you look at delta u, right? Delta u is uxx plus uyy. And let's look at uxx. What does it mean by uxx? Uxx means that it is a d dx du dx. So if you look at the discrete version, d dx u x plus 1y minus u x y. Correct? That's the discrete definition. And if you combine this one, it means what? It means u x plus 1y minus u xy minus u xy minus u x minus 1 y. Agree with me? Agree, anyone? Yeah, so this is the first derivative of the pixel on the left. This is the first derivative of the pixel on the right. And then the whole minus is the second derivative. And if you look carefully here, basically u x plus 1y plus u x minus 1y minus 2 u xy. That will be u xx. And if you use uyy, then it will be u x y plus 1 plus u x y minus 1 minus 2. Agree? And then we have to sum this. This is the delta u. Delta u is the sum of the ux and uyy. So, in other words, delta u equals to what? Yeah, so it will be u x plus 1y plus u x minus 1y plus u xy plus 1 plus u xy minus 1 minus 4 u xy. Okay, so imagine, if you want to imagine this, it's basically that you have a map. X plus 1 y, x plus 1 y is here, right? That one is x plus 1 y. This one is x plus 1 y. This one is xy. This one here is x minus 1. And then this one on the top is y plus 1 x. This one is y minus 1. Means that you have the sum of the left and right, top and bottom, and then minus the middle one multiplied by 4. Okay. Anyway, so if I divide this with 4, I remove that 4, and I divide this with 4. Correct? If I have this factor 4, inverse factor 1 over 4. And what does it mean by this? If I have to divide by 4, the whole equation here, what does it mean by that? Is this the average of the 4 pixels on the left, right, bottom, and top. So in other words, here, this one is the average. So this one is u average minus ux. Well, this one is the average at that location. Agree with me here? Okay, so we have the average of the surrounding of the pixels and minus u, and that's actually one of 4 nabla u. Any questions so far here? Because of this, then I can express the equation here. So this equation. So this equation, I can express this equation with the average pixel. I can use average pixel to express this equation here. So in other words, I can write down x u plus IYV plus IT multiplied by X minus alpha delta U equals to 0. That's the original equation, right? I remove 2 because 2 is meaningless. On the left, there is 2. I can cancel these 2 out. And we know that nabla delta U is alpha delta U, alpha average minus by U equal to 0. Yeah. 4 is gone. Why 4 is gone? Because I multiplied that with alpha. So alpha here is 4 multiplied by alpha. Alpha is a constant value anyway. Right? You can put alpha prime, and alpha prime is literally 4 multiplied by alpha. Okay, so I also have a second equation, IYV plus IT IY V square, or average of V equal to 0. Okay, so now we want to solve this problem. So this is the problem that we want to solve. Okay, so similar to Lucas and Kennedy, we can transform this equation into alpha plus ix squared iy ix iy lambda plus iy squared multiplied by UV equals to lambda u lambda v minus ix t iy it. I think that's correct, right? Okay. So then, unlike Lucas and Kennedy, what Horn and Skunk doing is, so this is Horn and Skunk optimization. Is that he tried to discretize this equation. So he tried to discretize this equation. Alpha plus, remember that Ix, we can have Ix, Ij. So Ij here is the pixel index. It's not patch index, but it's the full pixel index. Okay. So this is the discrete version of the previous equation. So I have Iy, Ij, Ix, Ij. So the derivative of the I in that particular pixel. And then I have Xij, Iyij, and I also have alpha plus Iyij squared multiplied by Uij, Vij equals to alpha Uij, the average the average of uij in that particular pixels. And it is computable. If you know u math, then you can have this average minus ixij, itij, alpha vij minus iy, ij, itij. So what's happening here is that everything is known except this one. This is unknown. You also do not know this one. This is also unknown actually. So this is the two parts that you do not know, but the rest are known. The rest are given. All right. Okay, so this is the solution. Then you have to do this u ij vij equals to alpha plus ixij square xij iyij xij iyij iy alpha plus iyij square inverse multiplied by alpha u. So I just copy this one because it's exactly the same. Okay. Oh, by the way, if you look at Horn and Skang paper, he showed all this equation here. He showed the derivation. Not as detailed as what I showed to you, but in his paper there is some long derivation of this mathematical equation. But anyway, so this is the equation here. But now, as we know that we have to deal with this invert. So we have to deal with this inversion here. And the inversion is, you know that you have A inverse. So if A equal to A, B, C, D, for example, then A inverse equals to 1 over determinant of A multiplied by D A minus C minus B. Right? So that's the definition of determinant inverse for two by two method. So first, determinant of A for our matrix equals to here, right? This one multiplied by that one. So alpha plus xij square multiplied by alpha plus iyij square minus xij square iyij square. And that one equals to alpha square plus alpha xij square plus alpha ij square. That will be the determinant of A. So with this determinant of A, then we can solve the inverse problem. So u ij vij equals to the one over the determinant alpha square plus alpha x square ij plus alpha iyij square multiplied by the new form of A, right? dA, so dA means alpha plus iyij square. This one is minus xij iyij ix minus ix ij iyij alpha plus I x I j squared multiplied by the rest here. Okay. Right. Oh, by the way, I deliberately show you all the detailed derivation to show you that this is research. Your master and PhD students. So normally people will just gloss over this and just give you the final output, right? The final equation. But that's not the way the research is done. Research means that you have to go every detail of the equation here. And that's the point that I want to make here, that you have to know the derivation. And sometimes the derivation is painful. It's long like this. But that's how people get into the solution. Okay. So bear with me, it's almost there. I believe before 8 p.m. we should finish this. So then we can have a break. Almost there, it's almost there. Yeah, so then let's look at UIJ, the solution for UIJ. V will be similar to U anyway, so I will skip V. I focus on UIJ. This one will be alpha plus IY squared IJ multiplied by alpha. So basically this one multiplied by this here, and this one here multiplied by that one, right? That will give you UIJ. So alpha average of UIJ minus IXIJ, ITIJ minus IXIJ, IYIJ multiplied by alpha V average IJ minus IYIJ, ITIJ. Right. So that one will be UIJ divided by alpha square plus alpha I x square IJ plus alpha IYIJ. Okay, so yeah, this one I think you have to do the multiplication, quite complicated. So I'll just skip that one because it's just very simple manipulation. So you end up with alpha squared reduced fxij minus alpha xij itij plus alpha iyij squared uij minus alpha xij iyij vij. And this one is divided by this equation here. And this equation can be simplified into alpha multiplied by alpha in that way. And then we can cancel this out. Right? Okay, so once we have this, then we multiply this side into the left side. And then do the whole derivation again. So I don't want to do that because it's just simple derivation, just algebraic derivation. But at the end of the day, if you do the derivation for the derivation, then you will have alpha plus ixij squared plus iyij squared multiplied by uij equals to alpha plus xij squared plus iyij squared multiplied by U average ij minus ix ij multiplied by iy ij bij plus ix ij U average ij plus ij. Okay, so what we are now doing is that we want to have this uij. In the end of the day, we want to have that uij. It's still some steps. Okay, so anyway, so I will not, because of the time, so I will not get into the equation there, but in the end, if you look at the later on, if you look at home, then we can express uij mu equals to this one here, the one on the left here, the one on the left here, go to the right. So in that case, you have uij average old minus ixij multiplied by xij uij average old plus iyij vij average old plus itij divided by alpha plus xij squared plus yij squared. Okay, so that is for U term. So this one is something that we will use in optical in con optical flow. So in the end of the day, it's iterative operation, and once you have in the beginning, you just initialize randomly, or you can use Lucas and Kanade for initialization, and only for the gradient that is not equal to 0, and then put 0 the rest. That will be the initial uij. And for example, when t equal to 0, right? So when this is odd here, when t equal to 0, when the iteration equal to 0, I'm not sure what iteration index here. So iteration index, for example, k equal to 0. So k equal to 0, which is odd, means that you have initialization value, random initialization value, and then u average means the average for that particular region. Remember that the average means that you have 3 by 3, and then you take the average of this 3 by 3, and that will become uij old, right? And that gives you old value, and you have all this value here as well. You have the uij old, and you have vij old, and you have I, the gradient of I. And then with this value here, you update uij for every pixels. And then you iterate this again and again until it converges. Okay. So that's the basic idea of this one in Skunk. So now the question to you is that where is the global optimization here? It seems to us that ij here is the local pixel, right? So where is the global optimizations going on here? Exactly, the average. So the average have domino effects. Over the iteration, this average become growing and growing. And that's how the optimization become global. Right? So that's that simple average in the beginning that we use for delta, actually the key of this global optimization. Right. Any questions here? Yeah. That's right. So again, U and V is the delta. So in the beginning, we want to have this. So we have so we have this u, delta u, uxx and uyy, and then we do the discrete operation. So this is the whole thing of discrete operation. And using this discrete operation, we found that this one is the just average expression of the sum of the surrounding.
So the average is not fair to like the top left and top right.
Yeah, so we basically, well, this one is one of the ways why we end up with the top and the left only and not on the corner is because our definition of this derivative. And the definition of derivative is not necessarily have to be in this way. It can also involve the corner pixel as well if you want. Right? So basically, that the message here is that in the end of the day, you just this expression of derivative or second derivative will involve yeah, so you have this sum here of the surrounding. That's the basic idea. And we can extrapolate that for the entire region. If you want to go into the strict with this equation, you can just use the form, not necessarily to be the whole patch, if you want to be strict. But I don't think there's any effect on that. Okay, any other questions? Right? Okay, so this is Horn and Strang, and this is the basic optical flow. I encourage you to look at the paper and then see how he explained this solution by the author themselves. Okay, anyway, so if there's no questions, let's have a break, 15 minutes. So we start again on at 8:15. Let's have a break again. Yeah, I would like to have a question. Yeah, for the but actually use oh, okay. Python because this one is last year. Because I think Python is more useful for you than Flash. Yes, actually. Okay.
So the alpha should be something like this have a parameter.
Sorry?
Alpha.
Alpha is a parameter. This is like
Hyperparameter.
the lambda in the previous discussion.
Oh, okay, okay.
So we have a weighting factor for prior.
Yeah. Yes. Something I said.
Yes, yes, something like that. Yeah, this one is I will remove it. I will change it. Yeah.
And this needs high GCO. How can we get the about the function in of the user? I can just learn it from the example.
Yeah.
But
There's no explanation for it, so you have to.
but I have seen a few actually.
So you can ask the GA. You know GA, right? Yes. Yes.
Contact.
You can use look at the luminance.
Have the information.
So any assignment questions should go to the GA. Yes.
So in the rectified images.
Yes.
Just forget that in this line, we're going to choose the parts to match to this parts, right? And you mentioned that we should use a patch to find better match.
Yeah.
But this match, does it mean like just a single row or like this one?
Patch is I don't know what you mean by this.
Just 5 pixels, you know.
Oh no, it's a 5 by 2.
Oh, so it's
Yeah,
like a
so
matrix.
5 is a 5 by 5 pixels.
Oh, so we're going to find matrix all along this line.
Yeah.
Oh.
Well, not this image, but the image. So this one is this one is the
Oh,
target.
I
This is the
see, I
source.
see. And according to this outline, are we going to do this in part 2 of the?
Yeah. Yeah.
Oh, I see.
Yeah.
Thank you.
Yeah. Yes.
One more question about the PA. So, you write imports PYGCO in the part one, but actually I finished make and install. I need to import the GCO.
So you ask the GA.
Okay, I scale about
Yeah. Yeah. Yes. Yeah, wrong typo. That's it's a last year construction.
We just use
Python. Yes.
But you mean is what the text
Hmm.
because you, and then let's say X bar is at the start, which is the could be the next zero to the max, but it's any other traditional
So the min and the max value are not fixed, but the number of this range is fixed. For example, 100. 100 will be fixed, but for the one in the corner here should be 0 to 100, but in the middle should be 50 to 0 on the left, on the right.
but if it's not,
Fixed in terms of the number, on the if it is 100, it's 100. If it is 50, if there is a 50 until 50, 0 to 50 on the right, 0 to 50 on the left, then right. So you just use the 51, and the rest.
so this will be applying to, let's say, for X, if then the max, then the value should be 0 to. Then if this is, let's say, is another pixel in the middle, it will.
Oh, I see your point. So here is the case. The width, for example, 100, right? 100 value. And then you from 0 to the width, for example, the maximum is 100. So, well, this one is for smoothness constraint. Smoothness constraint will be the same for every pixel because it doesn't really matter the value of the pixel. This one is only for smoothness constraint. But you have later on you have the theta term.
So this will just fix as, let's say,
Yes.
no matter whether.
Yes.
For the range.
It doesn't really matter.
Also happen to have the same spectrum on the stereo from rectified. So like for the data curve, it's just that or for the smoothness constraint, it's just that we take all the d main to dx, we just calculate the interval in the center, you get like the distance, and for like the data curve, we just cover the horizontal line. For example, if 0 to 100 is that we are looking at like 100 different positions.
Yeah.
So if the X is in the middle, then we take 50 on the right, 50 on the left. Oh, okay, I see. So this is the implementation, right? So it's 50, 50. Yeah. So then you don't have to like go all the way to the end of
So
the.
the label has to be fixed. The number of the label is fixed. For example, 100 people, 100. Yeah, but the value, I think that you don't need to be fixed for the data.
What do you mean? Don't need to be fixed for the data.
Well, you know, in the data term, for example, if the value is fixed, 0 to 100. Okay. Well, in that case, you still can, it's fine. For example, if it's 0 to 100, right? Because on the right and the left, on the right and on the left, I forgot the detail. So can you just ask because we have to check on the left.
Yeah, that's a must, right? So
Yeah, so then the value it's not consistent anymore. For example, 0 to 1 and then now become 50 to the right, 50 to the left.
yeah, yeah.
So what would be the format of the factor? So I don't really exactly remember the details, but you can ask the.
Oh, yeah. One more question is like, do we have to large enough fee so that we can like encompass
Yeah, all the four possible
all
values.
of the values?
But the interval, you can set the interval. You know, that's fine.
Oh, the strike we can try out
Yeah.
to find out.
It's been one.
Oh,
If this one, it will be good flow.
okay, yeah.
If your unit is close to
Yeah,
This one is not binary. This one is actually multi-level. But don't worry about that. It's already in the PIC under the package. The package will under the level. All right, so let's start again, second session. So the Horn-Scan optical flow will give you something like this. So this one is a Horn-Scan optical flow for different iterations, for the number of different iterations. So the first iteration, for example, if you use random value or 0, 0, 0, 0 everywhere, and then the first iteration will look like that one, which is not really precise. It's not global optimization yet because the average will not, will not have the domino effects yet. But after 128 iteration, for example, then it starts to be more dense. Okay, so the iteration here, 128, gives you more dense optical flow information. And this one here on the right is the reference flow, means that the ground truth. And this one is done in very controlled environment, so then you can have the ground truth. In general, to have the ground truth of the optical flow is very difficult. So normally what people do is to use synthetic images. Right? You use synthetic images, then you can easily know the motion of every pixel. But if it is in the real world, actually it's very difficult. Right? But anyway, so this is the results for Horn and Skunk global optimization. Now, the problem with this is that, as you can see here, it is not really that precise, and it is quite slow. When slow is fine in this case, but that's the main problem with Horn and Skunk global optimization. So every optical flow that follows Horn and Skunk has this problem of being slow, because you have to do the iteration until the domino effect can be applied for all pixels. And this only solved very recently with deep learning. So using deep learning, if you use deep learning, you have to use the synthetic data because it's very difficult to get the ground truth. And if you have the ground truth, it's just very simple training operation. You have, for example, UNet kind of architecture. You train with the ground truth, and then the UNet will give you optical flow immediately given a pair of images. And that makes the optical flow more applicable for many different applications using deep learning. But before deep learning, optical flow like Horn and Skunk here is something that the only option that people can have. And the main problem of Horn and Skunk is that it's noisy, as you can see here. It's not really smooth. Sometimes it can be very noisy and also inaccurate. And in order to solve this problem, I think exactly before deep learning era in 2009, I think, or 2010, or around that time, there is the paper, quite famous paper, papers called Secrets of Optical Flow. So, and we want to discuss this secret of optical flow. So basically, the secret of optical flow, try to find the fundamental components in optical flow and try to improve based on these components. So it's like a recipe books. So you try to get what is the important ingredients that you can improve further from this Horn and Skunk optical flow. The first component or the first ingredient is robust objective function. So Horn and Skunk, original Horn and Skunk use convex function, which is basically a quadratic function. And according to this paper, by analyzing the convex function, it's not really that good for optical flow computation. So they're more robust objective function than quadratic function. And the second ingredient or the key here is to have force to find a mechanism. Oh, by the way, although as I mentioned in the earlier of my discussion, that now everything is deep learning and it's quite fast. But actually, some or many components of deep learning are inspired based on traditional approach, based on this analysis here. Right? So, for example, robust objective function. In objective function, normally in deep learning, we have loss. And this loss is actually an objective function. And many people using quadratic or just, MSE loss. But based on knowledge on the traditional computer vision, some people change the loss into L1 or into something that is more robust. The same here, cost-find mechanism was originally proposed in traditional approach. But then this one is used also in deep learning approach. So recent deep learning approach, which is called PWC for optical flow, use this idea of cost to find. Okay, so learning this basic traditional approach computer vision will enrich your analytical skill. And this analytical skill is useful for deep learning because deep learning is treating everything is a black box. Without knowing the analytical skill in the traditional approach, it's very difficult for you to think further how I can improve the deep learning in terms of design and architecture. Okay, so please keep this in mind that the traditional approach is still very useful, even if your approach is deep learning. Okay, so the third ingredient is interpolation. Number 4 is median filtering or filtering in general. And number 5 is ray processing. And number 6 is GCC. GCC constraint. So we have BCC, which is a brightness constancy constraint, but we also have GCC, which is a gradient constancy constraint. So this is 6 ingredients, 6 important ingredients to make optical flow to be robust. To make optical flow robust and more accurate. Okay, so let's start with robust objective function. So as I mentioned again, the traditional point and scan using quadratic function. So how does this quadratic function look like? The quadratic function, for example, for the smoothness constraint, so you have nabla u, right? Remember nabla u? Nabla u is actually, if it is the magnitude of square is actually u x square plus u v uy square, right? So that's the degrees of nabla u square. And in this one is actually nabla u. So imagine that we have nabla u or just nabla u, or perhaps just u. Here is u. Any value of u, and then you have a function, quadratic function on nabla u. So this one is a quadratic function on nabla u squared. Okay. This one is nabla u. So in this case, yeah. So to be precise, I think I have to put this nabla u, so then it can be nabla u squared for your quadratic function. Okay, so anyway, so here the expectation is that the idea behind this is that if you have nabla u in this value of x or u1 here, then you will be penalized here. So this will be the penalty, right? So this one in the y-axis will be the penalty of that ui. I mean, if the delta ui, nabla ui is that location, for example, the penalty will be higher compared when the nabla nabla u1 here equal to 0. If it's 0, then there is no penalty. But if it is nabla u1 here, then there will be some penalty. And if it is nabla u2 here, so if you have nabla u2, the penalty will be higher. Okay, it's quadratic in terms of the penalty. And people say that this is not fair. Why it is not fair? If it is there's no noise, that is fine. The penalty is a deserved penalty. But if there is some noise, so the actual value of nabla u, the smoothness constraint, is actually this value here, and the penalty should be there. But because of the noise, so this one is nabla u, because of noise, nabla u1 prime here, because of noise, is moved to that location. And the penalty will be much higher than the actual penalty that should be there. So quadratic has some dangerous consequence. The penalty will be too high, will be too severe if there is some noise. So it's very sensitive to noise, especially if your actual value is here. For example, nabla ui or nabla u1 is actually there, but because of the noise, even though there's a small noise effect, so nabla u prime here is there, then the penalty will be very much higher. Higher than what it should be, much higher than what it should be. Okay, so the consequence is that the smoothness constraint become dominant compared to your data term, and then it becomes inaccurate because it's over smooth. Okay? So in order to deal with this, then what people do is to make it non-quadratic, non-convex. So one of the possible solution, because this one is something that we do not want, something that too much penalty is something that we do not want. So what we can do is to clip this function. So become the blue function here. To clip. So the function that we apply is not quadratic function anymore, but becomes truncated quadratic. Okay, so truncated quadratics means that you have this kind of function. So you truncate that, the penalty will not be too high. Okay, so there is a truncated quadratic, but as you can see here, it's no longer convex. So what is the definition of convex? Convex means that if you have this function, convex function here, like a quadratic function, if you take 2 points inside this function, so 2 points inside this function, for example, it will never cross the line. It's never crossed the. That is the definition of quadratic. But if you use non-quadratics, for example, I put two lines here, it will cross the line. So this one will cross the red line. So that means that if it's crossing the red line, it is non-quadratic, non-convex. But if 2 points inside the function never touch the line, never touch the boundary, then it is convex function. Okay, so that's the difference between convex and non-convex. Convex function is easy to optimize, but non-convex is much more difficult to optimize, to get a global optimum. But this is something that we need to sacrifice, because if you use a convex function, the penalty will not be proportional. So that's one is called truncated quadratics. Another function that normally used and popular in optical flow is called Charbonnier function. So Charbonnier function is something like is somehow convex and non-convex at the same time. I mean, it can be convex and it can be non-convex depending on the hyperparameters. So Charbonnier function is something like that. So the expression is that f of x, actually x squared, which is quadratic, plus epsilon squared power to a. So when a smaller than 0.5, then it becomes non-convex. So when A is more than 0.5, then it will be non-convex. So normally what we do is A equal to 0.5. That's what people normally do for optical flow. Any questions here? So again, we have to use non-quadratic function so that we can have more proportional penalty for our error function or loss. Okay, so that's one thing, one recipe, one secret. And the other secret, the other ingredient, is cost to find. Okay, so the modification of this cost to find algorithm is that in Horn and Skunk algorithms, right? The optical flow is very sensitive to the large disparity, large movement. So if the movement is very, very large, for example, 100 or 200 pixels away from one image to other image, the optical flow computation will likely to fail. And most likely that you need to have more and more iteration. And it makes the computation very, very slow. So that's the main problem of Horn and Skunk, that if the disparity or the motion is very large, then it's likely to fail in the computation of the optical flow. So how we can deal with this? So the basic idea is to make it in what we will know as pyramid images. Right? So pyramid images means that, let's see, so if you have large image, for example, two large image, then we have to downscale the image. And we also need to downscale further. So in the downscale images, the distance, even though in the original the disparity is large, the motion is large, but in the small images, the distance will be reduced. So that's the basic idea, that if we in the small scale, then the disparity will be reduced. And with this one, we first compute the optical flow, U and V. U and V at that scale. Of course, it's not really precise because this is a very low resolution, right? But we don't really care about the resolution at this point of time because what we have to handle is the large motion disparity, and this small scale can deal with that. Right. So once we have that, let me think. Right. So right. Okay, good. So once we have U and V, so U and V here means that U and V here means that you can register every pixel from image A to image B. So you can actually find the motion of every pixel of A to every pixel of B. It means that you do the alignment between image A and image B. So if you warp image A with U and V, then every pixel will just overlay on top of each other on top of B. So the overlay of the image A, warp image A, will be on top of image B, exactly on top of it, right? For every pixel, I mean. So with that idea, for U and V, actually U and V is belong to A. So we apply U and V. So U and V here, you have U map and V map in that scale. And then, for example, for U, you enlarge this. You enlarge this U. So you enlarge this U in the same size as C or A2 here. Put it A2, A1 and A2. So we enlarge U into the resolution of A2. And the same as we enlarge V in the same resolution of A2. But of course, original U is much smaller than the resolution of A2, right? In that case, we just make it bigger and then do the interpolation. It means that, so for pixels, if we have 4 pixels, for example, this is from the original U, you have that pixels, if you enlarge, then you have these pixels here, right? And these pixels, actually, this is U11, for example, U12, U22, and this one is U21, for example. So the location, you enlarge this. But of course, you do not know what will be the value in between, right? So that's the problem of enlarging or upscaling your image. In this case, you upscale UV map. So you have this problem, what is the middle values? So because we do not know the middle value, so for example, imagine that UV here is represented by this black magnitude. So the black magnitude, so let me draw again. So this is called interpolation techniques. So this one is the A2 size. And we want to know what will be the value inside here. And this is the value of U from the smaller scale or the causal scale. Right. Okay, so that's the value that this one is the value of U21, this is the value of U11, this is the value of 12, and this is the value of U22, right? That value is actually at this location, but you do not know the location in the middle because you don't have the data, right? And the simplest way is to use bilinear interpolation. This one is called bilinear interpolation. And there is a better way of doing the interpolation called, this is bilinear interpolation. By doing this bilinear interpolation, then you can know the value in the middle. But there is a better way. So for example, if it is your higher resolution pixels, and this one is your optical flow in the coarser scale, in smaller scale, then what you need to do is to have bicubic interpolation. Bicubic interpolation is something like this. Make it more curvy. And if it's more curvy like that, it would be more robust. So you see, instead of bilinear interpolation, we use bicubic interpolation. Okay. So by using this bicubic interpolation, now you can make your UV map into higher resolution map. In that case, then you have UV prime. UV prime is the enlarged version of your original UV, right? And then you do the warping. So here you use UV prime to warp A2. So warp A2. If you warp A2, it will be much, now what happens is that you will have much closer image to B2. So you have B2, you have A2 prime, and A2 prime is much closer in terms of the object motion compared to A2 to B2, I mean. So there is a distance, so A2 to B2 compared to A2 prime and B2 prime, the distance here is much smaller. because you warp that image with your UV, your estimated UV from the previous image, from the smaller image. Is that understandable? Okay. So once you have this warp here, right? So when you have warp version, then you compute optical flow between A prime and B2. So this one is your second UV2 map. So UV2 is much more precise than UV1 because UV1 is an optical flow for smaller images and UV2 is larger images. And it is not the interpolation version, it's already the actual optical flow between A2 prime and B2. Okay? And you repeat this process means that you use UV2 to interpolate. You enlarge this one, so you enlarge this UV2 prime. UV2 prime. So UV2 prime is the larger version of UV2, and with that larger version of UV2 prime, you do the warping here. So warp A3 using UV2 prime. Okay, and then the warp here of A3 become A3 prime. And again, you have a closer image to B3. And then you do the computation of UV optical flow 3, which is between A3 prime with B3. So this one is computed from A3 prime and B3. Is it clear? So you do this again and again for every version of these images in the pyramid, for every level in the pyramid. So it becomes more and more precise, the optical flow. So that's called cost to find. Any questions here? Yes.
Why does the IQ more about kind of linear?
Yeah. So well, this is not really that big deal, but barrier of interpolation means that this one is a linear interpolation. Means that if you want to fill up this value here, it has to be linear value between the two values here, right? But bicubic is not linear. It's following a certain curve, and it's likely the value here is not linear. In natural world, the motion between one point and the other point is not linear. It's likely that it's not linear in the real world. Well, it's not necessary, but it's better than linear. Of course, you can have a better interpolation techniques. But in this paper by Secret Optical Flow, they found that bicubic is better than bilinear interpolation. But whether there is a better version of interpolation is a question mark. Right? People don't really further investigate that particular interpolation techniques. A lot of different interpolation techniques in the world. Okay, any questions here for cost to find? Okay, so I already mentioned about three things. So I have mentioned about robust objective function. I mentioned about cost to find mechanism, and I also mentioned about interpolation, which is in this case bicubic interpolation. So median filtering is another way. Median filtering means that once you have this optical flow for every pixel, so this one we have optical flow UP1. So in this case we have UP1, and then you have UP2, you have UP3, right? For every level you have optical flow. So the idea of median filtering is that for every version here, you apply median filtering. Median filtering is very simple filtering. basically, if it is average filtering, you take a patch. For every pixel, you take a patch, and then you average. And then replace that pixel in the middle with the average value of these neighboring pixels. Right? That's the average filtering. Median filtering is that instead of finding the average, you try to find the median. Right? The median means that the most value in the neighboring pixels. So and then you replace that pixel in the middle with the median of the patch. That's called median filtering. So the same here for UV, for every pixels, you replace with the median UV from the neighboring pixels. And in this case, it will be more robust to noise, because the noise will be suppressed. Okay, so that's the idea of median filtering. So that's number 4. Number 5 is called pre-processing. I will defer this one next week. This one has something to do with texture and structure components. And texture and structure component is a bit complicated concept. I will explain that next week. And maybe GCC, I will explain this next week as well. So basically, this one, you have IX and IY, and GCC is that we want to make sure that even the gradient from one and the other image are the same. So if you have this object bottle again, so, not only just the intensity that have to be the same after you move this object, but also the gradient of these pixels have to be the same when you move the object. So why GCC is a good idea is because, if you just rely on the brightness constancy constraint, that this brightness here is the same as the brightness here, what happens if you have an object like this object? If this your light is on the top, I put an object on here, for example. Sometimes you are inside the shadow, sometimes you are outside the shadow. Right? If it is the light is on the top, and the object is below or beneath some object, the shadow will be there. Shadow means that it will be darker. So the intensity of these two images will be different, and BCC will fail. But GCC will not, because the gradient under the shadow and the gradient outside the shadow will be the same. So that's why under this change of illumination, GCC is more robust than BCC. So that's the basic concept of GCC, that the gradient of your pixels should be kept, should be constrained. All right. So that again, we will discuss that next week. Any questions here? Any questions, anyone? Okay, so if there's no questions, that's all today, and I will see you again next week for the continuation of this optical flow discussion. Yeah, thank you, everyone.
A simple question about the